Okay, so let me welcome you then to this lecture. As I said, today we will go through the storage part to finalize the storage part. So in the last lecture we roughly started with the replication schemes. So to show you this picture again, mainly focusing only on the DHTs, so all this random and selective placement, which are the unstructured networks, this rendezvous networks, and the super peer networks. Those we didn't cover, so we only had a look at the key-based data storage. And then we had to look at the different replication schemes. So either this very simple one with the full replication, and then with the erasure codes, where we had seen that the erasure codes allow us to get more availability for the same ratio of replication. So if you have 3 times more data elements stored, or data or storage space taken, then we have a much higher availability. Or to say it in different words, if you want to keep the same availability, then we need less overhead storage for replications. So this was some very nice feature of it. So that was the benefit. And the drawback was that if you want to change the content, this is getting difficult, because then you have to replace all entries. So we had the example with 100 and 517 data blocks. And if you have split your data object in 517 pieces, then you have to gather them all to replace them all, and this is quite expensive if you want to modify it. The simple replication is easy to modify. There you have to only contact the number of replicating nodes and ask them to change it, and that's it. Then we had to look at how we can make sure that the replicas are available. So if we have this 517 data blocks replicated, how can we make sure that there are still sufficient blocks available? So let's say in this example it was 100 we need, and we have 517 as a starting point. And the easiest solution is to periodically check all of the blocks, and if there's some missing, then replace those. This is very expensive, both for probing and also for for replicating, because with that you maintain a much higher replication ratio that you actually need. The other part that was presented was the lazy maintenance, where you have this threshold. So that's the magic word here. So do you have this repair threshold, and you have again this many blocks, and you again probe the different replication nodes, and you only replicate if you are missing a specific number of data blocks. So this number of missing data blocks have to exceed the threshold in order to have the replacement. That's good. So it's you don't replicate all the time, but when you replicate, then you have a peak in your traffic. It's easy, and but it needs also to have some so it can be used as somehow an attack point, but it's easier, it's at least better than the naive approach. Then there's this randomized lazy, where you do not actively probe all the data blocks. So there you already save something. So the lazy maintenance, you have to probe this 517 copies, and here you just probe as many as that you need to find 100 successful copies, 100 blocks. So that was the example. So we need 100 blocks to restore the data. We had 517, and here you have to just have a look to find 100 available blocks, and all the missing blocks on the way that you find. So if this purple blocks were missing, those you have to replace, and let's say these are 12 or 15 or so, and all other 400 you don't check, so you save on the probing costs. And this, in comparison to the lazy approach, is still as sufficient and still leading to that high availability, but at lower costs. And comparing to the naive solution, it's also much better. Okay, today we want to have a look how, now this after this theoretical approach, what kind of P2P storage systems have been proposed and what kind of main ideas are available. Yeah, can we have a look at? So one very simple solution that came out quite early is by the same people who also proposed CORD, so Jon Stoiker and the people of MIT. And here the main idea is that you use, so the main idea we will come later to, but what is the purpose? So you have a read-only system, you have only one publisher, which can write the data only once, and later on it can be only read. And also here, instead of files, we use blocks. As we have seen, that has some advantages, so in terms of load balancing, and if you have more blocks, then they are somehow distributed to the nodes and one single node is not overloaded. This is good, and there are some evaluations that show that still as efficient. And also we have currently in several cloud systems with distributed data centers, they use also similar concepts to have a large scale, easy to extend data storage. Okay, let's see what they do. So what are the goals? Of course, it should scale, so you should be able to add new nodes, you should be able to add new storage space. It should be it should keep the data available under normal churn. So if half of the nodes fail, then data will be lost. So, but under normal churn, it will be okay. It should balance the number of files on the nodes. It should try to really distribute the traffic load and the storage load on all nodes. Data should be inside, some quotas could be implemented, but the main goal was just to have this file system functionality with load balancing and availability. Okay, so what do they do? So the main idea is that you have a file system, and it's this is to the main operating system the access point. So it provides a file system API, like it's known from operating systems, and the implementation itself is distributed. So for the operating system or for the user, it's not obvious, it's transparent how it's implemented. And all files are blocked, so chunked in blocks, and they have this application or add-on for CORD called dhash, which implements this block storage and data storage aspects. And CORD is the old CORD with some small modifications. So instead of one successor, you have R successors, so that you are better connected to your neighborhood. Okay, then you have they also introduce some different roles, but they are not too relevant, because so we have either clients which host data and can access it, and the servers are just used for storage. So this is the blind and dumb nodes that can be easily added. Okay, as I said, the data is split into chunks. For load balancing, it's distributed to more nodes, and also traffic is better distributed to all nodes. It's also replicated. Each block is replicated R times. And then we have two kinds of blocks. The one is the content block, addressed by the hash of the content. So this is a very general concept. This is occurring in several solutions. So that you take one data block, you hash it, and the hash of the block is its object ID. And the reason is the following. So if somebody else hashes the same data, or not the same data, but comes to some blocks with the similar blocks, or same blocks even. So just assume you have a large data file which has lots of zeros in it, or don't know, so which is somehow partially empty, and this single block that is taken out of the file is similar for other files as well. Then you would result in the same object ID, and if you want to store the data into the network, you would see, oh, there's already some object with the same ID, and that means it's exactly the same content. So you really can know if there's already some content with that ID, that's really the same. So you don't have to check the content otherwise. So if the hash is the same, then it's the same. So that you can reuse blocks for different files. So that's the main idea. And now, if you have this distributed blocks identified by their ID, by their hashes, you somehow have to bring structure into them. You have to know which blocks belong to which file. And this is done by the root blocks, which is modifiable by the content, by the owner of the file system. So you have a root signed block, so which is derived by his public key, so he can verify that he was the one that that changed it. And in this root block, he can encode which data blocks belong to which files. I better show you some visualization before I go into detail how it is done. So you have the entry block. So if you are the root of this file system, you have the entry point, this is your root block. This you can sign, that you show, okay, this is really the object that I created. If somebody wants to modify it, if there are some attackers, then you can check, okay, this is really the one. And then you have different entries. And this is a block, a directory block. It's also a content block. It contains further pointers. So you have either content in it or a pointer. And also the pointer list can be interpreted as one content block. So if you want to, for example, store a picture of you in this file system, then you would first split the picture into different blocks. You would create for all of these different blocks the hash and store the blocks into the file system. This is easy, that we can do with DHT. We just store the block, small data content, under its object ID, which is its hash. Okay, this is doable. Then you create a new block which tells this is a file, a picture, and it is containing this block and this block and this block. So here you list the block, the object IDs. So if your picture would be split up in 10 blocks, then you would say maybe some metadata, this is a picture, a file name and something, and then you would list the 10 block IDs. So that if you would have this file, you know what kind of file it is and you know where to look up the blocks. This is the main idea how to store a file. And the same you do for directory. So if you have a directory, then you have some metadata like telling what is the directory name. And then you have object IDs which tell which files are in this directory. And you might also have a further pointer to other subdirectories also. So you have basically these 2 points of data items, either a real data block or a data block with pointers which somehow create your file, your tree system, so your trees in your file system. And this is all static, so these blocks you will never be able to change. But what you can do is to change the entry point. So to tell, I have a new, what you can do is to get to the entry point, and if you, let's say, want to replace a file or to delete a file, then you would modify the directory and just take out the pointer to that file. It will be then still in the system, but nothing is pointing to it. So this is how you would delete a file. Or if you would add a file, then you add first the content blocks, then you add the file block telling which content blocks belong to it, and then you would make an entry. So you would create a new directory block which has the additional pointer to that file, and then you would update your root block to not link anymore the old directory block, but the new one. I hope this is understandable. So to go back what I wanted to say, so what we have is we have very simple solution, very simple functions. So we can store a block, and we can get the block, and we can modify the root block. or we can also store a signed block. And what we have is we have the starting point with the root, which is signed by us, so we can verify it's really our data. And that was the important part. Every block that we store is read-only, except the root block. There we can introduce a new one. So by introducing a new one, you can also either to take over your old directories, then you would change nothing, or you introduce one new directory block which contains a different entry for a file, for example. So this is how you can do it. So you always have to rewrite your structure of your file system in order to make a modification. And as it was said, so the root block has pointers to other blocks, and there are also like the directory block and the file block, which can either contain the real data piece of file or something like a further pointer to a directory or to a file. And because if you would leave it like this, then data will be stored forever in the network. Even if you delete it, you would just delete the pointer. So you need some kind of garbage collection, and this is done by the concept of storing it only for a finite time. So let's say a few days. So that means if you don't update these data blocks within these days, your data is lost, and all elements which are not linked to from the root node, the data, those elements, those blocks will be leaving the network. So you have to periodically, every few days, you have to refresh your data structure file, so your file system, your data tree, to tell it should not be deleted. Yeah, that was the picture that I was showing. So the day of this tree structure, and this is the big idea that you should keep in mind. If you want to write a new file or to modify some entry in a directory, then you have to create new blocks which have new pointers and which your root element points then to. So you have to so as I said, if you enter a new file, then you have to create the file block first of all, and then a new directory which is referencing to that file, and a new root block which is referencing to the new directory. So you always can only write, and you have to leave it to the system to forget the unreferenced data items. Any questions for that? So this is the main idea, is really to take with you is we really work with these blocks as non-modifiable. So once they are in the network, they cannot be modified. So we can only modify the first element, and it has to point to some new elements if you want to make some changes. Okay. Yeah. Okay. So to summarize, as I said, so first we have to, if you want to add an element, first to write, and later on we can only just write to make modifications. That's a very common concept, that we store the block under the content hash. That really allows to reuse blocks and reuse data elements, and to check for existence without really checking the content. If we can just check if there's an object under this ID. We have only one publisher in this concept, which can change the root document, no one else. But he can check the validity of it, because he can sign it, and he can verify his signatures. And we don't have this explicit deletion operation. We just have to delete all links to that block, and then after a few days it will be deleted. Okay, now let's turn to some other peer-to-peer based storage system, which basically takes a totally different approach than this immutable, non-changeable blocks. So Ivy, also developed in the same group, and also based on Chord. But this is basically the second big approach that is taken if we talk about modifications in network. And let's see what are the goals. Also here they want to have some network file system like semantics. Users should be able to modify files. But now what we have logs. What is a log? A log is a description of what has been modified. So that would be something like a patch or a delta information for a file. So if we talk about text files, then it would say add a line at point, or add the text at line 90. It should be written this and that. So you really have at a very low level this change commands, how the data file should be changed. And these logs, so you don't have just one log, you can have several logs. If they don't interfere, that's okay. So it's really like a patch for a piece of software where you can have different patches applied for the same software. It's also having a look at different writers. So we can have multiple writers which are distributed, so they don't coordinate themselves. And then the question will be about which data and which action maybe is to be done first. So this is the question of consistency. Consistency means that if two nodes in the same network look at the same data, do they see the same, or do they see different results? An example is if you have two very distant nodes working on the same data, and the one makes a change and the other one makes a change, then what is their order in which the change should be performed? Because we don't have a synchronized clock around the world, which everyone can use as exact timestamp, and they can see, okay, I executed my change command 1 millisecond earlier, then my should be first. So we don't have this synchronized clocks, so we don't have the synchronized data exchange. So there are always some changes overlapping, and the question is which changes should be done first. One solution typically for consistency and also for versioning systems at one time was to lock the file, to say I'm now working on it, nobody should be able to modify it. It's not very attractive, because sometimes people forget to unlock and then the data is locked for all time, and it could help, but it's not really attractive. Also, there's the idea that we cannot trust people and machines can be compromised, so we have to consider to allow some undo function. So if there was some error in the execution of a change or a patch, there should be able to have an undo function. And also if the network separates, so we have then two big networks which are not connected anymore, then both separate systems should be working, and once they merge again, then also the changes should merge again. So comparing this requirements, especially with the collaborative file system from before, this would not work. So if our data blocks should be stored at the other network, then we would not know what's happening there, and if some changes should be done there, then the network would not be able to solve it. Okay, so what do? So they, as I said, in Ivy use logs, and this is a command for modification, like add a line here, or delete a line there, or add a so it's really like in coding, like in a patch. And they maintain both the file system and the metadata. This is like file name and size and current timestamp and so on. And now every participant has his private view on the network, and the private view is defined by the set of logs that he considers. So if we would think about the file system, then we would have for each file some main starting point, and then which modifications have been done on it. And now my personal view would then be which of these modifications that might be in the network available which of them do I know, and which order do I consider as correct. So the nodes might be distributed in network, and they might have different logs. They might have missing some log, and so that's why they have this personal views on how from the beginning object the changes have to be done. And what they can do, so they can only write their own logs, so they can only say, I changed the data with this modification, and the ideal state is that they can read the logs of the others and consider those changes as well. Okay, and we have also this order, so which action came before which, so this is a timely order, so which tells really in which order the logs have to be done. So in very contrast to the collaborative file system from before, which only had the current snapshot, somehow there was only one current valid snapshot, that was the one that was linked from the root to the final blocks. Here we have very many snapshots of the data, or versions of the data, just depending on which modifications you know about. So how does it work? So each user, if he makes some changes, modifies the log of that specific file or directory list or whatever we talk about, and the others should get to know about it. So they should learn about it, and then and when participants agree on a view, they say at this, so all this set of changes we consider as a new begin, as a new current status. These entry points, what modifications I have that's not changeable. So this is the root entry basically, and it contains the basic entry points for all participants. And what do we call then a snapshot? A snapshot is a selection of logs that we consider as our private view. So in order to not always look up the whole network about what's the current status, we copy all data that is relevant to us, that we want to know. This is a snapshot of the network, and this we consider that we work on. So that we collect once and then we work on it, and maybe we collect the newer logs on it, but this is the starting point what we use. And this contents of the snapshot should be mainly the same for all participants. So at one time they all independently collect their snapshot, the current copy of the network basically, and use this as a basis, and then only consider the new logs for it. Yeah, so they get all logs recent, which are in the network currently, and then they can create a new version for themselves that they use to not question the network anymore. And if the new user comes in, then again he has to or she has to get the basic data element and all modifications. So it really takes a lot of time to pick up to the current state. Something similar is also okay. So here you really build a lot of on this logs, and the question is, or the benefit is, that people can independently work on documents. So in the previous section we only had one writer, because if he tells this is a new file and I modify the directory block to add the file, then that's the valid new block, and if somebody else made the change somewhere else, then it would be overwritten. So there's only one view in the previous collaborative file system. Here we can have different views. So if you have different network, then a separated network, then they can work independently on their logs and their improvements. And once the networks meet or the users meet, the logs can be combined. So if they do not interfere with each other, So if they edit the document or whatever it is, they edit the file at different points, then it's like a merging of two source codes of the same type. That might work out quite fine. In order to help this merging, what it has to have is to have first a sequence number to know, okay, in which order they are. But this is just local, so I mean that doesn't help globally. And on second point, it tells what it is based on. So how is the relationship to other logs? So to be able to identify an order of logs. So by comparing the version vector, so what other logs do I know about and what's their current status, that can be used to introduce, even if different people combine their logs, they can create some semi-order on it to really identify which modification came after which. Okay. And in any case, if there's something concurrent, or if there's some unclearness what should happen because they are conflicting logs, then there's some rule, so to order it by public of participants or so. So that really resolves the status globally on the same way. So it might be unfair for the one who has a big public key, so his changes will not be considered as frequently as for those with a small public key, but at least if the same merging is done on different parts of the network, it will result in the same outcome. So this is the nice thing, that you can really work independently in the network and combine this modification logs. Okay, so this is Ivy. So it really works basically on the logs instead of final unmodifiable data blocks. Okay, now the last one that we have a look today is Ocean Store, and this introduces a further concept. Oh yeah, let's see. So history, it's from the people from Berkeley. It runs on Tapestry. Tapestry is almost exactly the same as Pastry, little modification, but it is very similar. So, and it allows also to modify objects in a less drastic way than we had here. So we don't have the overhead of this large log lists, and we don't have the missing, so we are more flexible than the block-based collaborative file system. So what it was aimed at, it was thinking at that time, 2003, 2004, that in the future we will have this Internet of Things, many intelligent devices that are everywhere, and they have to be connected, and they wanted to have some persistent information storage for all these small devices that are very slowly but coming. And they said they wanted to really support some at that time large-scale networks with very easy storage and retrieval on distributed devices. Later on, the cloud came up, but that was that was prior to it. They also wanted the people to pay for it. It's a little bit interesting for peer-to-peer networks, just to tell as a side note, in order to finance it, but didn't take off. And what was the idea? So first they assume untrusted infrastructure, so everything should be encrypted, and they should be also considered that there's a small minority of attackers. So those they also wanted to address. And what they also wanted to have is multiple users that participate in the network that want to write or delete, so really multi-user writing. And they considered somehow most of the servers are working correctly, but not all of them. And they have a very small number of servers that are trusted to follow the protocol, but they don't get the data. So they introduced two kinds of roles, so the peers basically, which are responsible for the storage, and they have some second kind of role which is in charge of deciding which modifications are valid and which are not, so which are in charge of access control and modification checks. Okay, it should be very flexible, so that doesn't tell anything. Okay, so how is it looking like? So here also objects have unique identifier, and they are replicated and migrated, so copied along the devices on the fly. This is nothing new, but the replication has two concepts which is applied. So there's a fast algorithm, which is really probabilistic, which tries to distribute the data quite quickly, but not for full availability and reliability. And there's a slow and deterministic algorithm if the first one fails. So first probabilistic quick one, which will work out in 90% of the times, and a slower one, which works if the first one is not successful. Okay, so we have two types for replication and two types of data types. Here the data is considered to be either active, that means for active data changes are allowed, and there's an archival read-only version where changes are not allowed. And the nice thing about it is, so here for the archival, here we can use erasure coding, which is space efficient, so we don't need too many nodes to store it. But the problem with erasure codes was we cannot easily change the data, but this is fine. So if we have a read-only version for this archived data, that's good. So I mean, that's defined to not be able to change. And if you use erasure codes for that, that's doable. So this one is fine. And for the active, there's another approach how to store it and how to deal with changes. So that's what we will have a look at. First of all, also here we have self-certifying object names. So it has different information coded inside. So first of all, who's the owner, also a human readable name, and also a hash of the object. And that allows to also the object naming allows to have directories and to define a more general usage of it. So it's not just simple data blocks, but we have a little bit more advanced data elements like this data items with metadata in it, so about owner and who the have a real name and to use it for directories, and also who the owner is, and so it's up to the user where his entry points should be. So there's no real user-specific entry point. So he can say this is my entry point and I'm happy with it. How's it with the access control? So they assume that all nodes might be untrusted. So all data is encrypted, and the encryption is implemented by having one key that is required to read the data. So if you encrypt your data and you store it in a network, then it's up to you to give the encryption key, the decryption key to the read-enabled users, otherwise they cannot access it. If you want to revoke a read permission, so if some of your friends or whatever should not be able to read it, then you have to re-encrypt everything and don't tell him the key. If somebody wants to write, then you have this access control list. This is not commonly known. Access control list, which lists who is allowed to modify the data. So this you can also specify. And now the question will be, how do you check? So whom do you give the rights to check whether the writer who wants to modify the data is in this list. So if it's only one node, then it would be probably very easy to have an attacker there, and then he can do quite a lot of damage. So we need to introduce a concept how security is supported in presence of several attackers in the network. So we must not have single point of failures, basically. And we will come to that. So just to see how the mechanisms for the location is done. So first we have this probabilistic algorithm, which is very easy, which is very simple, similar to this expanding ring. So the main idea of this expanding ring was that popular items are found in your neighborhood. So also here you just place the data in your neighborhood and given the structured network a little bit a hint where you can find it. And here we use Bloom filters. So on the next slide there will be a small outlook how we use Bloom filters for that. But it is very unstructured, so it's really about something like a random walk that you try to find it in a short range, your data, and if it's not available then you give up. And the deterministic algorithm uses tapestry, which is really like pastry. I think the difference is in pastry you have this prefix based routing, and in tapestry you have this postfix, so you just turn the IDs around and then you have the same. It's also deterministic and it's guaranteed to find object because you have the DHD function to find it under its object ID. So this probabilistic one is more like a caching. So you spread the data a little bit around you and you give a little bit more hints where people might find it. And to talk about the multi-level Bloom filters, this is a very summary again of Bloom's filters. So what it can check is either to give answer as no or maybe. And we had this concept of we have an array of k bits and then hash functions. So I will not go into detail for this, but what we have is this attenuated or multi-level Bloom filters. Did we talk about this already? Do you remember? I think not. So I think I left it out. So what is an attenuated, so erweitertes Bloom filter of depth d? So we have of level d. So first, so it tells you. So okay, so to tell it differently, the 0th level Bloom filter is the Bloom filter for your documents. So you can put all your documents that you have into that Bloom filter to encode it, and then people can check whether you have it not or you have it maybe. And the ith level Bloom filter is the union of all Bloom filters as distance I. So for the first level Bloom filter, you take the Bloom filters of all of your neighbors and you make the union out of it, and so die Vereinigungsmenge, and then this is the first level Bloom filter that you have. And the second level, then you take the first level Bloom filters of all of your neighbors, or the 0th level Bloom filters of all of your second top neighbors, and then you also merge it, and that's your second level Bloom filter. So you always have this ith Bloom filter is the union of all Bloom filters at distance I. Why is it good? So it's good because let's say you have 20 nodes as neighbors, and then you are looking for specific data, and that was the goal what you wanted to have with the quick and dirty, or quick and fast solution, to try to find it in our surrounding, and if we don't succeed in a short amount of time, then we started the deterministic lookup. So what it tells us, if we have 20 neighbors, it tells us in this direction of the different neighbors what kind of data might be. So if I look into the Bloom filters of my neighbors and I'm looking for a specific file pattern, and out of these 20 nodes, maybe just 5 have it, then I know, okay, for this 5 it's more probable that the data is located in that direction than it is located at the other 15. So it helps to redirect my random walk to find the data. And then a query, so is a random walk rooted on the edge. So it's walking around the way where the probability is highest to find something. And the shortest way, the probability is bigger if the Bloom filter is matching at a lower level. So this is an example how it looks like. So here we have yes. Okay. Okay. So these are in these fields below the nodes. They are the Bloom filters of level 0. So this is the data that they have. So let's say N3 has the object X, and this is the Bloom filter it has, and N4 has this Bloom filter, and N2 has this Bloom filter. So what they do is they send to N2 their Bloom filters of level 0, N2 calculates his Bloom filter of level 1, and yes, and from the perspective of N1, this would be the Bloom filter of level 1, so that's the union of all of his neighbors, so only 1, 1, 1, 0, 0. This is the level 1 Bloom filter of N1, and the level 2 Bloom filter of N1 is the union of all of its 2-hop neighbors. So if you take the union of 1, 1, 0, 1, 0 and 0, 0, 0, 1, 1, then you get this. Yeah. And now by this way N1 would learn how the probability is that the specific object he's looking for is in that specific region. So if you consider this to have it with 20 neighbors and their neighbors, then you get a quite good information which of your neighbors are more promising to have the data or not. So this is for the quick solution to look it up. So we were at Ocean Store, yes, that was the probabilistic algorithm. So it's a little bit tunable on how often you replicate the data near you, and it uses this multi-level Bloom filters with the small, very short random walk, attracted by the probability to have that the neighbors have the data. And if the short random walk does not succeed, then we go for the deterministic algorithm with the real lookup, and then we look for the real location. Okay, now the question is how do we update objects? So we were talking now about getting objects that are already in the network. The question is how do we write objects and how do we update objects in the network? Okay, also here Ocean Store works with something like logs in order to support distributed editings of the same content. But it's a little bit more advanced. So it has first a list of predicates. That means the requirements, what is needed for an action, for an update to be taken to take place. So the predicates is something short. So this is something that you can check before making the change. It's, for example, you can check whether the basis object that you want to make the change on has the same version, has the same size, has the same block or whatever. So you can really check before, so you can define only make these changes if this and this requirements are true. So only if the basic version that is going to be changed has this specific size. So that makes sense for patches to data objects, because if you don't know what you change, then you shouldn't maybe. So you can really specify first what should be the basic that you want to apply your change on. And now these predicates can be evaluated, and if they are correct, then the change can be applied. So you can modify that object, and if no predicate is true, so if it's not valid, then you abort the action. and there should be some logging what has happened, so that there was a change or that there was an attack or invalid change. Okay, what kind of options can we have? So either to replace the block, insert a block, delete a block, append a block. This is well defined now. If there's some encryption, then it's easy to add and replace, a little bit more difficult for insert and delete. This is for, I don't want to go too much in detail about the encryption because it can be complicated. Just from the main ideas, what you should take with you is that we also use here the same kind of blocking idea like in the collaborative file system. So we also here we have some index blocks which contain pointers to other blocks, and we also replace the old block with an index block which points to the new block. So we have also this list, but it's also more advanced by having this log idea where changes are only performed in terms of these patches, in terms of these logs. So it's combining both aspects to get on one side this always clear vision about what is the current state of the data item. That was the good thing about the collaborative file system, so we always knew what is the current status. And on the other side, to have this support for having changes on the same data by multiple people. There the logs were quite good. So the logs help there to really define at what requirements the changes should be made, and if two people have independent changes on the same data, that's okay. So it's really supported. So still something is missing. So how do we replicate? We were telling there are these active and archival replications, and now for the active change, so for the changing of the active elements, this is also secured by an additional step. So typically in this collaborative file system, you just change it and that's it. So you overwrite it, and also with the IV, you just do it. Here, because we have multiple users writing at the same time, there's some control level introduced, and they do it by having a second level of peers, a dedicated role of peers, which are trusted to follow the protocol, and they should decide whether your change is valid or not. This is the main idea. So you have the primary tier, which decides using a Byzantine agreement protocol, which I will explain in the next slide. So the main idea is they decide in a majority voting whether your change is valid or not, and if it is so, they tell the second tier, everyone else, to perform this modification and to replicate the new data. And if it's not valid, then they can say don't do it, there's some malicious attack or so. So we have this trusted first group which decide on what needs to be done, and the second group, the second tier, which stores all the data, and some of them communicate with the primary tier, and among each other they flood, let's say, epidemic algorithm. That means so they just unstructuredly communicate with each other, and they flood the changes. So what is the reason? So we can assume there are a few trusted peers. They should be able to decide, but they should not be overloaded with storage. So they should not take part in the storage, but they should coordinate the storage and allow decide what is allowed and what not. So this is typically very small and well connected, and the other one is somehow unstructuredly connected and storing. So what happened? One moment. Before I go to the Byzantine generalist problem, just to tell how it's working. So if a node in second tier, where every node is basically except the few trusted ones, but most of them will be in the second tier, he wants to make a change, so he creates his modification and tells it to one node in the primary tier, and tells, okay, this is what I want to change, and he already starts replicating to some random peers at the second tier. So he doesn't wait for the answer, he just starts to replicate to have it available. Now, the update in the primary tier, they decide about it, and if they agree it should be accepted or rejected, then they flood this result and ask everyone to consider it. So if they accept it, then the replicas are forwarded randomly, so somehow semi-flood. It's not really flooding, it's more randomly sending it to your neighbor with some specific probability. So it's just semi-flooded. Okay, so and if there's a positive result, then all nodes will be informed through multicast so that everyone is involved. Ah, yes. Okay, I think that was the point that I went over a little bit too hastily. So the node starts replicating without waiting for the result, and this is done by sending it unstructuredly around, so just on a probability basis. And once it is accepted, then we have this update flush, where really the result is pushed to all nodes and they can replicate it. Okay, then the question is, how do they, so what is the Byzantine generals problem? So this is, do you know that? Sometimes very popular. It's not very popular. It's popular sometimes in computer science lectures and security. No, so there are some typical computer science problems that during the time you might hear. It's one with the philosophers at the dining table. Do you know that? Okay, good. So this is sometimes occurring if you have a if you listen to security solutions, then this sometimes occur. So what is the background? So there were some divisions, army groups of the Byzantine army surrounding an enemy city, and they had individual generals, so each division was led by a general, and they sent messengers around to communicate, so they were distant from each other at the different spots of the city surrounding, and now they need to decide on a common plan. So they all look at the city, and now they have to come to a conclusion. But some of the generals might be traitors and working for the other party, and they can send false messages and try to take influence on the group's decision. So the question is, if nodes, they can communicate everyone with everyone, but how do you come to a conclusion? So none of them can say, this is what the general opinion is. So the Byzantine generals problem is, I think I don't go into detail how it is solved, just what it's provided, what it provides. They can decide on a plan. Doesn't matter how the traitors behave, and it's required that we have at least 3 times more valid. Yes. So we have to have at least twice as many good, 3 times as many good nodes as. One moment. Yes, I think so 1/3 is allowed to be traitor, and at least 2/3 plus 1 should be a good general, and then the loyal generals can agree on a plan how to follow the orders. So even doesn't matter how the 1/3 of traitors behave, the good generals can agree, and that's then the majority. So you cannot have it for 50% or 51%. That's a little bit, so if you have only 51% of loyal generals, that's not doable. But with 66 plus or 67%, you can do it. Okay, yeah, maybe I should have prepared also how it's in detail, but it's a little bit, that would be requiring many slides. So just to take this as an idea and to look it up, well, how the generals work it out. But what we take as from this problem is that if our small group of primary tier nodes in OceanStore have at least 2/3 of loyal and good nodes, then they can really agree whether to follow the protocol and to accept data changes according to the plan. Okay, and this is for the active data. So you always have this second tier nodes which store the current active data, and this is flushed, and the primary tier decides on it. And the second type of data archival is this deep archival with erasure codes. There are different ones how to use it. They generate these data fragments. It's created by the primary tier, and it's distributed among the secondary tiers. And like we saw with the erasure codes, you just need a specific number of blocks out of this many blocks to recreate it, and this is very space efficient. Okay. There's some option when to deep archive data, or whether every version should be archived, or whether it should be less frequently, but this is tuning question. So the takeaway message for today is we had a look at these three types of network storage of the peer-to-peer based storage systems. So the one was the collaborative file system, which used the static blocks to store the data. Yes, and every time you wanted to change something, you have to recreate the blocks, you have to change the pointer blocks until you change, and then recursively to change the blocks that were pointing to that blocks that you changed until you change the final roots document, and you have always the current snapshot. Then we had to look at Ivy, which basically works with this modification logs, how the data have to be changed, and there you have this your personal view, which logs you take into account and which not, and the nodes try to periodically agree on a snapshot that they consider as this is the current status. And then we had Ocean. Ja.
Ist da ein Unterschied zwischen Logheads mit Finished und Logheads ohne Finished?
Nein.
Der Loghead ist ja die Datei, die man findet. Die Grunddatei, die Grundlog.
Ja.
Und dann folgt das ja der Zeit nach. Wenn jetzt der Loghead points to the most recent log, dann müsste der rechts sein. Und wenn die Loghead
Okay.
ursprüngliche Datei ist.
Okay, also dann komme ich mal hierher zurück. Da müsste es eigentlich stehen mit dem Version. Die Logs enthalten ja auch, auf was sie sich beziehen. Genau, Version Vector. Also die enthalten erstmal welche Nummer. Sie sind also, jeder versucht das hochzuzählen für sich, und er beschreibt, auf welche Version, auf welche andere Logs es sich bezieht, also wie sein aktueller Stand ist zur Änderung. Und dieser Pointer, der verweist quasi auf die vorigen Versionen. Ist ein bisschen, also ja, also man kann sowohl also wenn man zeitlich darstellt, dann wäre das nicht richtig. Wenn man das abhängigkeitsbasiert darstellt, dann wäre es richtig. Ja, also dann würde der Loghead auf die aktuellste Version verweisen, die dann auf die vorige Version verweist, die auf die vorige Version verweist. Von der Zeit gesehen her würde man das in die andere Richtung dann betrachten. Also man verweist... Bitte? Wo? Aus der vorigen? Irgendwann. Mit einer Grafik? Okay. Okay.
Irgendwann nach der Abbildung.
Ja. Moment.
Ursprünglich eine Loghead-Datei gemacht wird,
Ja.
auf die alle anderen Veränderungen basiert.
Ja, also okay, ich verstehe, was Sie meinen. Also dass diese Ausgangsdatenobjekt auch, ob das auch Loghead heißt. Ja, ich gucke halt, wo die es haben. Also, okay, die Frage ist also, wo ist die Ausgangsdatei? Also, wenn wir jetzt das so betrachten, dass... geht das? Ja. Ja, da kann ich nicht weiter schreiben. Okay, also wenn wir eine Ausgangsdatei haben, dann würden wir das zeitlich so darstellen. Ich mache mal hier nochmal ein. So. Also wenn das die Ausgangsdatei ist, dann würde es von den Abhängigkeiten so sein, dass das nächste Objekt darauf verweist, dass es sich darauf bezieht. Und wenn es da wieder eine Änderung kommt, dann würde es sich auch darauf beziehen. Also dass man die so nachzeichnet. Das ist die Ausgangsdatei. Zeitlich gesehen wäre das dann ja aber so, dass das so kommt. Also das ist eben die Darstellungsweise, wie man das darstellt. Also entweder zeitbasiert oder halt abhängigkeitsbasiert. Ja, doch, schreiben Sie mich dann ruhig an. Ich ändere die Folie dann gerne und kläre es nochmal auf, aber das ist so die Hauptaussage, die man mitnehmen soll, dass man eben immer auf die vorherigen Versionen verweist, um klarzustellen, wo im Kontext das Ganze einzuordnen ist. Genau. Okay. Alles klar. Gut, dann sehen wir uns morgen und morgen ist auch der Ampf da und dann besprechen wir auch, wie der Simulator nutzbar gemacht werden kann und wie das alles schön aussieht. Bis morgen.